Okay, let's take example number 4. So you're given a table with time and velocity quantities. So first things first is we're gonna draw a velocity time graph for Marlo's cart, and then we need to answer following question. So before we can answer that, we need to have our graph. So I'm gonna do a sketch of my graph, well, as precise as possible. So velocity in meters per second, and then my x-axis pertains to time. That should be in seconds. And there should be a common starting point for both velocity, so the origin at 0, and that is always at the point of intersection between the two axes. And then to create my grid for my time, so I'm just gonna look at the minimum and the maximum value. So the maximum value is 6 seconds. So maybe perhaps I can use scale of 1 second. 1, 2, 3, 4, 5, and then 6. So 1.0, 2.0, 3.0, 0, 5.0, and 6.0. So if you can see, since I already placed the time and the unit, or at least the symbol, I don't have to place the second each time when I place in my x-axis. And by the way, for the title, you could just say V versus T. And now for the velocities, so maximum is 30, minimum is 12. But if I'm gonna use the same scale of 1 meters per second, that would be, well, it cannot fit. So I can, again, the rule in making a graph, you can actually use a different scale for the y-axis. It doesn't have to be the same with the anything that you use in the x-axis. So in my case, I'll be using 5. So that means each line represents 5 meters per second. And if you can see, since you're using a scale of 5, so the distance of that should be the same as the next one, because 5, the increment of 5, that would be 10. So if you can see there, of the same increments, so therefore the distance in your graph should also be the same. So make sure that you're going to do that. So 15, then 20, 25, and then you have 30. You can extend to 35, but 30 is enough, okay? Now I'm gonna plot each point. So you have here 0, 12 meters per second. So that would be in between 10 and 15. Again, don't worry if you cannot essentially locate in your scale the exact value of 12. You can approximate. Just make sure that you're gonna try to pinpoint as precisely as possible. Again, I don't have a grid, or I don't have a graphing paper here, so it should be expected that somehow there might be some difference in my drawing. But since that is 12, I cannot also place that particular point in 15, okay? So it should be in between 10 and 15. That's my point. So 1 second after it's 15, that would be somewhere here, okay? And then 2 seconds after it's 18, so 18 is just below 20. And then 3 seconds after it's 21, so it's a little bit over 20. 4 seconds it's 24, it's just below 25. And again, you can just do approximation. And 5 seconds it's 27. And then you have 30 for 6 seconds, okay? So now to draw the graph, again, I'm just gonna draw an average line. So as you can see here, your average line doesn't necessarily perfectly hit all of the points, although that would be an ideal case. Then again, okay. So this would be my average line. It doesn't have to be a line that hits all the data points. And again, you can extrapolate both to the lower end and then the upper end. So you can place two arrows. And now we can actually get the average acceleration. So for letter A, to answer letter A, acceleration is just equal to the slope. And then the slope is again just your y2 minus y1 all over x2 minus x1. So you're going to choose 2 points. Again, in choosing the 2 points, it must be any point that is being hit by the particular line that you made. Again, don't worry if, again, the line that you made doesn't necessarily hit all the data points that you have, or the actual data points. Okay, so, well, this one here perfectly hits that one. So that's my P1. That would be 0 and 12. Okay, and then what else? Maybe this one here, it hits the line. So this is my P2. And that would be 2 seconds and what's that? 18. Okay. But then again, you can also use other values. That's okay. But in my case, I've chosen that one because it hits the line. So maybe I cannot use this, okay, because it doesn't hit the line as well as this one here. Well, that is in my again in my graph. Maybe it's different in your graph that you made. It's also okay, as long as again you're using any 2 points along that line. That must be the thing that you need to remember. So now I now have my P1 and P2. So I'll be using that one to solve for the slope. Y2 pertains to 18. So if you're wondering, where did I get that one? That's my Y2. That is here. Subtracted with Y1. What is my Y1? Y1 here is 12. So Y1 is 12. And then my X2 is 2. Okay, so if you can see, that's my 2. That's my X2. Subtracted with the X1. X1 is 0. So that should give me an answer of positive 3 meters per second, right? So 3.0, the least number of significant digits here, or significant figures, is 2. So therefore, final answer should have 2 significant figures. And again, positive pertains to north direction. So yeah, I'm just gonna, well, it doesn't specify in the problem, but I'm just gonna set that one as my north, as my positive. Okay. So therefore, you express your answer as 3.0 meters per second squared north. Again, I replace the positive sign with the direction, okay? So north direction. So it must be, because the question is acceleration. So that means both magnitude and direction, both magnitude and direction. So, because in some cases, you might be asking for the magnitude. So in that particular case, you can just answer 3 meters per second squared. So again, the magnitude have the number plus the unit. So if you just answer number, well, that is incorrect because it must be with a corresponding unit. Okay, so magnitude is this one here. So that's your magnitude. If you can see both magnitude and, well, both the number and the unit. Direction is again represented by north. So your final answer should have the north, not just positive 3 meters per second. Because positive, again, we just use the positive or negative sign to express the sign when we try to do our calculation. So you just use, or you need to replace in your final answer. Now, for letter B, calculate for or determine the displacement of this car during the 6-second time interval. So that means that it's from 0 to 6. Okay. And to answer letter B, well, based on our discussion earlier, the displacement is just equivalent to the area. Okay. The displacement is just equal to the area. Okay. Area under the curve or under your graph. So that means that the area, again, when we try to create the area of the graph, it must be from, well, it's from 0 to 6 seconds. So therefore, our last point would be at 6 seconds. And then we will try to get the area, all of the area that is being shaded here. So what would be the area of this part? So again, you stop at, again, this is the x-axis. So again, when you try to get the area, if you're wondering, where should I stop? Well, you're gonna stop at the, towards the x-axis, okay? So that would be the displacement. So the area of that. And if you can see the figure, it's actually a particular figure that you can divide into 2, right? That means that this is a composite figure. You have a rectangular form, and the other part is, this one here is triangular form. Okay. So to get the area, the total area of that, that would be equivalent to the area of the rectangle. So that would be area of the rectangular part plus the area of the triangular part. And, well, depending on the figure that you made, remember that the area is calculated differently, but I guess you are quite familiar with that. For the area of a rectangle, it's base times the height plus, that would be for the triangular part, it's base times the height divided by 2. Okay. And if you can see, both of the base is 6 seconds. You can see this is the base. For the first one, this is the height, that is 10 meters per second. And then for the height for the triangle here, this would be the height, that is, well, is that 10? Sorry, that should be 12 meters per second. And then for the other one, that should be 18, right? So the height of the triangle is 18 meters per second. So if you can see, if you're gonna break that one down, just try to remember the dimensions also changes. So again, for the triangle, you're adding the triangular part and the rectangular part. So the base would be the same for both. Base is 6 seconds multiplied by the height of 12 meters per second plus the base is again 6 seconds for the triangular part, but the height is 18 meters per second. And if you can see, somehow it gives us the unit of meter, which is to be expected. That is our expected value. Okay, so area is just equal to, well, I'll not be rounding off here. I'll just give this is 72 plus what this be 54, right? Okay, so if I'm gonna add that one, this gives me 126, and it's positive meters. Well, remember that displacement again is a vector quantity. So therefore, if it explicitly asks for the displacement, it must be both magnitude and direction. So therefore, the displacement is equal to, well, if I'm gonna express my final answer in terms of this number of sig figs here, it's 2. So that would be 130 meters and then north. Okay, so the final answer is 130 meters north. Again, this is in 2 sig figs. It's the same as the least number of significant figures in our data. Okay, before we proceed to example number 5, are there any questions with this example here? Anyone? So, okay. If there's none, again, if you can see for the displacement, it's just the area. So again, area, since you're talking about velocity and time, so therefore, usually the figure that you can create in our case will always just be a combination of triangles and rectangles. So just try to remember that triangles have a different way of getting the area, and the rectangle is also different. But if you can see, yeah, rectangle is just base times height, and the triangular part or any triangles is base times height. So it's base times the height divided by 2. Just try to remember that. Again, have different formula. And I try to break it down just to show you that, well, since this particular figure is consist of, I can break it down to a rectangle or a triangle. That's why I'm trying to add them, get the individual areas of each figure. Okay. Okay, let's proceed to example number 5. The graph below shows the velocity of a pigeon in the sky. And if you can see, somehow this is a little bit sinusoidal in nature. So I'll just gonna, in this case, well, let's say for example, I use east as my positive direction. So that means that negative direction is west. Okay. So anything there, anything that is below zero, since there's a negative value, so it should be west. West. And again, positive is east. Again, I use east as positive, so therefore the opposite of that should be the negative direction. So I'm gonna get the instantaneous acceleration at 10 seconds. Okay. And if you can remember, in getting for the instantaneous acceleration, that is the slope of tangent line. I.e., in this case, well, in this particular case, you have t is equal to 10 seconds. T is equal to 10 seconds. Okay. So you're going to create a tangent line, therefore. So if you can see here, somehow the acceleration at that, because there is somehow a change in the magnitude. Maybe there's no change in direction in this particular case, but there should be, well, clearly there's a change in magnitude. Somehow it slows down. Maybe you can say you have a point from 0 to 10 that's a straight line, but hardly. But you can make a point, but somehow at 10 seconds, there's a change. There's a little bit change in the magnitude. It slows down. Then it went slows down considerably. Maybe stop at one point, and then yeah, move in the opposite direction at around maybe before 30 seconds. So 10 seconds is somewhere here. So that means that we're gonna get a tangent line at that particular point. Okay. So you use a ruler and create the tangent line. In this particular case, again, we might have a different value for the tangent line. Again, that would be understandable. But just try to remember the meaning of a tangent line. It's a line that only hit once. So I can create this particular line here. Okay, so this is my tangent line. So I'm gonna get the slope of that. So what is the slope of that? So again, in this slope calculation, it must be, I'll gonna decide first the 2 points from that particular line. So let us say that I'm gonna make this one as my P1. Well, it's close to 20. I'm just gonna use 20, so 0 and 20 there. And then my P2 would be, yeah, we're just gonna use this one here. It's P2 would be 10 and 60. Okay. So after which, if you have decided that using that 2 points, again, don't worry if you have done this one independently and somehow get a different value. Don't worry. It's part of, yeah, because what I did here is also approximating that particular tangent line and just do the approximation. Again, I did my best to create a line that only hits that particular point. Okay. So for the slope, again, it's just y2 minus y1 all over x2 minus x1. So in my case, y2 is 60 subtracted with the y1 of 20 all over x2 of 10 minus 0. Okay. Oops. Yeah, 0, 0 is green. Okay, just using color coding here for this is 40 over 10. So the slope, therefore, or the instantaneous acceleration is equal to, well, yeah, it's just one sig all throughout, or I'll just use this one here, 3 sig, so that would be 4.00. It's positive meters per second squared. And again, always change from positive notation to the direction. So I've used here positive pertains to east, so if you can see. So therefore, positive sign means east. So this should be 4.00 meters per second squared east. Again, if you're wondering why is it is east, well, I assign positive value as east. And again, it asks for the instantaneous acceleration. So it is asking for both magnitude and direction. So my final answer should contain both the magnitude and the direction. Okay.